Assalamu alaikum students, hope you all are fine. I am Mohammad Assam Siddiqui with the lecture number 4 and week number 3. In the previous lecture we have covered the properties of the fluid, although we are unable to cover out all the properties. So in this lecture we will move a bit faster what we actually moves in the previous lectures, because I will try my level best to cover out you the remaining properties of the fluids, and what the course content we have to cover it in this lecture we also completely cover that content. Okay, so please pay attention a lot in this lecture, because from now you will understand how complex the fluid mechanics is. Okay, we straight away start with the surface tension. Surface tension is not a very complicated property. I just want to explain all these things in the whiteboard. The literature you can easily go through it and you can easily understand by yourself. It's not a very complicated thing. Actually, normally if we place any fluid in a container, so the container actually, let's suppose we have a jar, okay, and I have placed certain amount of water up to certain level. Okay, now you can see that the molecular arrangement of the liquid are in a manner that this molecule is present here, here and here, in that way. Okay, let's suppose the other molecules under the surface, under the interface, or you can say at the surface of the liquid, are arranged in that manner. Okay, if we close look up to a bit lower layer present to this interface, their all forces are balanced to each other. Okay, this molecule is binded by all four sides. Again, this is the molecules also binded by all four sides, and all this are arranged in that manner. But when we come up to the surface molecules, they are not binded by all four directions. Okay, they have forces with the three directions. They are binded, so there is a single unbalanced side present at this part. Okay, on the behalf of that, the molecule present at the very surface bind together with more attractive force rather than the molecules present at this layer or in the more bottom layers. So these molecules offers greater attractive forces, and on the behalf of that, this tension occurs, which we so called as the surface tension, because this tension is only exists in the surface molecules. So we call it as a surface tension. And we can say that this unbalancing of the force, intermolecular force, that the molecules at the surface are not binded from the foresight of their own. On the behalf of that, this unbalanced force led the surface molecules to bind together with more intermolecular forces, rather than if we compare the intermolecular force is present at the layers lower than the surface layers. Okay, so this surface unbalanced force is categorized as the surface tension. Okay, so surface tension is just nothing. Furthermore, is that it is also called as the surface energy or the surface of coefficient, and which is represented by sigma s, and its unit is Newton per meter, as we say that this is the force, unbalancing force, which is exists in a particular unit length. So this is so called as the surface tension. So I have demonstrated a bit with the figures as well. You can see the surface molecules are banned here and do not allow this insect to sink down and lift, balance its weight with the surface tension force. Okay, then we move forward to the surface tension present in the drop or air balloon or the soap balloon. So there is a difference between these two factors. Actually, when you see here that if I will talk about the droplet of water, how it generates, actually when there is a tap or a faucet which is partially leaked, so what happened, the molecules start to fall down, and on that falling to, they do not directly fall down to the ground, they actually made a certain amount of weight. That weight overcomes the surface tension, and then the weight, when further weight is increases, then the droplet is fell down to the ground. So let's suppose this is the size of that droplet. Okay, and your droplet make a shape of a spherical type of thing. Okay, there are two types of forces bind it. One is the water and solid surface force, which we categorize as adhesive force, solid surface force. Okay, due to the attraction between the solid water molecules and the solid surface, the molecule present here is bind with the surface. On the other hand, the molecules present in that part and in that part are in a contact with water intermolecular force binding. If we closely look this spherical droplet, what we find is there are molecules present at the center as well. There are molecules present at the surface as well. Similar manner, these the molecules which are not in the surface, they are bind themselves in all four directions. Although when we see the surface molecules, they are bind with the three directions, and again there is an unbalanced force available at the surface molecules, which is also responsible for the shape of the droplet is spherical, because it's not a square, because of the high surface tension between the surface molecule. Okay, let's suppose I only took the half size of this droplet. Okay, this is the complete droplet, I say, and I cut it off in a half manner to check how the forces are balanced to each other. Okay, so it is something like this. There is external pressure applying on the surface, okay, and there is a internal pressure as well. So all these internal and external pressure applying on this half surface with an area, and the area will be equals to as you can see here on the whiteboard that definitely there is a pressure inside the droplet, and there is a pressure outside the droplet, which is the atmospheric or surrounding pressure. And if they are balanced, the droplet would not spread up, and they are balanced just because of the presence of the surface tension force. And this surface tension force is applying over this complete circumference of that part of the droplet. So we can multiply it with the 2 pi r. On the other hand, the other force, which is the change in pressure, which is applicable on this complete area, okay, pi r square, which is circular. So when both these things are balanced, the droplet won't spread up to the environment. So we equate it, pi r square is equals to surface tension into 2 pi r. This can be balanced it up to, sorry, this square will cancel out this r, and we can say that the change in pressure will be equals to twice of the surface tension over the radius. This is for droplet. Okay, if we talk about the air bubble or soap bubble, which we form by using the soap liquid or detergent liquid and just push it with some sort of air, and the balloon is appears. So that shape is quite different. Okay, similarly, if we make a cross section of soap bubble, it is like that. The inner part, the air is present, then there is a layer of the soap liquid, and at the outer part again the air is present. Okay, so again there is an inside pressure of the balloon and the surrounding pressure of the balloon, and which is applying over the area of this complete circular part. Okay, so we can say that this delta P multiplied by pi r square will be the one unbalanced force, and the second force which balance out the balloon, balance out the bubble, is the surface tension. And here there are, as we know that the inner part air is present, and similarly the outer part all the surrounding is contained by the air. So there are two liquid layers present in this case. Okay, one at the inner part and the second at the outer part. So we can say that this surface tension is applied twice to the circumference, 2 pi r. Why? Because one circumference is inner one and the other one is the outer one. So there are two circumference at which the surface tension is active. Okay, now we can equate both these forces, because if the bubble exists, these two forces will balance each out. Okay, so delta P will be equals to pi r square, and which is equals to the surface tension applicable on 4 pi r. Okay, pi will cancel out, r square will, there is a power reduces, so the change in pressure will be equals to 4 times of the surface tension over the value of r. So these two results you will find for respective bubble, and you can easily understand how we can resolve the surface tension under different conditions. So we again move towards the presentation side. Here you can see these are the two actual figures which you can check out, because my drawing is not as good. So you can check the correction in this figure as well to understand it. There is a table present here which listed up the surface tensions of different liquids. We can say we can see the trend of the water surface tension along with the temperature, and definitely it is reducing with the temperature. Then we have glycerine and some up with soap water as well. So you can compare that the soap water has a very low surface tension as compared to the normal water at 20 degrees centigrade. Okay, so these are the respective surface tensions. Now there is a numerical which you need to resolve. Okay, in this numerical what you have to do is you have placed an steel ball or an aluminum ball over the surface of water, and you want to know at which diameter these balls won't sink, and it is only be done if the surface tension applying on the surface of the water surface or on the surface of the ball in such a manner that they balance out the weight of the ball. So what the data they have given us, we have to determine the maximum diameter of the steel ball. Okay, they have provided us a temperature 20 degrees centigrade, and you have also determined the diameter of the aluminium ball as well, an aluminum ball as well. Okay, and they have given you the densities of the aluminium and steel ball respectively. Like this is 7800 is the density of steel. So again we move forward towards our whiteboard side. Okay, here you can see okay, I have prepared the data. The temperature is given, the surface tension you will get from the table which I have represent on the slide, and this is for water. Okay, now we will balance out that how the force acting on that. There are two forces, one is the weight, okay, and second is the surface tension. The surface tension is equals to force on unit length, and it is applying over the length of total circumference of the ball, half circumference of the ball. So we can say that Fs is actually applying over 2 pi r. The halfly dipped, so it's apply on that complete circumference in order to resist it from sink in the water, sink down in the water. So you just need to balance it. Okay, Fs will be equals to 2 pi r and surface tension. On the other hand, the weight is the force which is applying downward and force the ball to sink down into the liquid, which is equals to the specific weight multiplied by the volume of the ball. And we know that a specific weight is equals to the density multiplied by g multiplied by volume of the ball is 4/3 pi r cube. Okay, and we need to determine the diameter, so we will reduce it in the form of diameter again. So these two forces which need to be balanced out here in this numerical, so we develop an equation in which we will equate Fs is equals to W, which implies that 2 pi r surface tension will be equals to the density multiplied by value of g 4/3 pi d cube over 8. 4 ones are 4. 4 twos are 8. I should also reduce this equation in the diameter form. Okay, so it will become like pi d. So I just wrote here the d, and we come up with a solution. It becomes to a square, it will cancel out, so the reduced equation will be something like this, that the diameter of any ball, if you are determined that it won't sink down, will be equals to, as it is in square, so we take the root, these two becomes 6. Okay, pi will be cancelled out. Okay, and the surface tension is present here, although these two factors will be divided by this complete factor rho multiplied by g. So this is the general equation you will find, and for solution, if you want to take the solution of respective balls, so you will have to just to put change the value of surface density respectively. Let's say if you are calculating this for steel ball, 6 multiplied by, this is the surface tension of water, 0.73 multiplied by density of steel, which is equals to 7800 multiplied by 9.81, and you will get the respective results, like 6 multiplied by 0.073 over 7800 multiplied by 9.81. So it will be like 2.39 into 10 to the power minus 3 meters. This is diameter of the ball for a steel ball, and similarly for aluminium ball, you just change the density of the ball, which is now becomes 2700, and we will get respective result, which is 4.07 into 10 to the power minus 3 meters.